I'm aware that I'm the only thing that stands between you and lunch at the moment, so don't worry. I will just stop talking if I run over, and you can go for lunch. So, yes, thank you. I'm currently doing a PhD at University of Dundee, so I look at deep learning applications within proteomics, which is a sort of like a biomedical field, studying the proteins in the human body, which is very interesting. But we have very many mass spectrometers that generate very, very high dimensional data sets. So I get to use deep learning on them every day, and somebody pays me to learn. That's pretty cool. Previously, I did my data science master's at the University of Dundee, which is really, is a really good one, actually. I recommend it. Might be biased. But prior to that, before I ended up back in academia, I did about 4 years in industry, so I've worked with all sorts of data, traffic data, customer engagement data, retail data, and originally came from a maths background. Actually, when I came out of my maths degree, I decided I wasn't going into the technical industry. So I'm not sure how I ended back in the technical industry, but I'm really enjoying it, so what more can you ask for? So, just before we get into things, I just wanted to quickly talk about machine learning as a definition, because everybody has a different one. So for the context of this talk, so I classify deep learning as the study of, multi-layer, complex neural nets. Machine learning is obviously the wider subfield, I would say, with the shallower versions that we've had working for decades, or statistical modeling techniques that we've had working for decades. And then, for me, that sits inside the wider field of artificial intelligence. But do you know what's funny? People will debate this until the cows come home. So that's fine if you feel different, but for the context of this talk, we're going to talk about machine learning in a more general sense, particularly more shallow networks. So, hyperparameters, what on earth are they? The favorite definition that I came across was parameters regulating the design of the model, in comparison to weights and biases, which are going to be the primary parameters of said model that you build. So this is actually one of my favorite textbooks that I'm quoting here, Neural Networks and Deep Learning. It is a bit math heavy, I'm sorry. However, if that's your thing, I highly recommend it. If anyone has not heard of the Iris dataset, have you been living under a rock? We're going to look at it today as an example because it's nice and straightforward. Everyone pretty much knows it. It's low dimensional, and we've got 3 clusters which separate fairly nicely. And what we're actually going to look today is about how the hyperparameters and their tuning changes the classification effects on the boundaries surrounding these clusters. Here's a couple of comparisons. Same model, same data set, slightly different hyperparameters. You can see that there is a change on where those decision boundaries sit. When I say decision boundary, I mean where we cross the line from one classification area into another. And so at that point, the model flip-flops and it says, okay, you're no longer in the yellow cluster, you're now in the pink cluster. Almost all machine learning algorithms have hyperparameters. I think I've come across one that doesn't. So they're quite vital to get to know. The good news is, before we go any further, most of the best libraries that you'll use for machine learning have best practice defaults set for your hyperparameter values for a given algorithm. And that's really useful as a place to start, but they really need to be adapted to the problem space that you have and how that interacts with the model that you're choosing to use. So you can see on the left here, we've got wider, looser boundaries, particularly in the yellow and blue regions. If you're colorblind, that's the middle and the bottom sections of the graph. And these change as we change our value. So this is a hyperparameter called C, which is a sort of regularization term. It penalizes misclassifications in the model. And so as such, boundaries wrap tighter around the data in comparison. So this is easier to see in animation. So this is a support vector machine, and we're changing that parameter C. And you can see actually the boundaries, particularly around the middle cluster in the yellow, change and wrap more strongly around the data. Now that's fine if that's what you want it to do, but actually if you would rather have a more general approach like this, how it starts, then that's going to be a problem for you. We're looking at this over a log uniform scale. Most people are not quite keen on logs, and I can tell you, I was the same. Actually, as a mathematician, I probably shouldn't admit this, but I didn't really understand logs until about 2 years ago. So I hope that kind of makes you feel a bit better. But we sample this parameter in particular on what's called a log uniform scale because we're interested in magnitudes. So applying the logarithm will transform our value into basically its order of magnitude. So if you have the value of 10, you log it, it'll go to that's magnitude 2. 100 would map to magnitude 3, and so on and so on. So what we're interested here in this hyperparameter changing is how the magnitude of the hyperparameter, whether it's 10, 100, 1,000, how that affects the boundaries of the model. And actually a lot of hyperparameters need to be tested in this way. They need to be tested uniformly on that log scale to understand the magnitudes rather than sampling along a more continuous distribution. An example of a continuous distribution would be something like the value of k in k nearest neighbors. So for anyone who doesn't know, k nearest neighbors, when it's going to classify a new case, it's going to look at the 10 closest, 20 closest other cases and probably average out their classification and say, well, what's it most likely to be? And so varying your value of k, so do we look at 3 neighbors, 4 neighbors, 5 neighbors, that is going to be your hyperparameter. And you can see in particular, the interesting part is actually the collision of the yellow cluster in the middle with the blue cluster at the top, because there are some overlapping data points there. And actually most of our algorithms show interesting behavior as they wrap around those overlapping points. And these are the parts in an everyday data set that are going to be really important when it comes to decision boundaries and making sure that they're appropriate for your purpose, whatever your model is predicting or monitoring, because this is how we can potentially overfit to our data a bit too much or underfit, actually. So another example is a random forest. It's one of my favorites because it's a good all-rounder on a lower dimensional data set to get an idea, to get a general idea, actually, of a classification. And so you can vary the number of decision trees. Random forest, for anyone who doesn't know, is just a collection of many, many decision trees. And they vote on what they think the answer is, and majority wins. And I kind of like this idea because I like the idea of all these trees standing around going, me, I think it's this one. And that's how I remember it. So actually there are many hyperparameters that come as part of a random forest. However, what we're varying here is the number of deciders, the number of trees in your forest that vote on the results. And this has an interesting effect on the decision boundaries, particularly in the yellow middle cluster and the pink lower cluster, because you can see this sort of flip-flop where the yellow part decides it wants to be horizontal, it wants to be vertical. And you can imagine if you had some outliers that were scattered down towards the bottom of the graph more or on the left-hand side, that could get a bit dicey for you. There are a bunch more hyperparameters actually that come with decision trees in general, as I said before. So they are good all-rounders, but actually you can change them quite a lot, which is a good thing and a bad thing. A good thing because you can be in control, but a bad thing because preset defaults might not be best for your data set. Excuse me, and you might not get a reliable idea of model performance. So, final example, good old multi-layer perceptron. We are varying another regularization parameter here. Almost all machine learning algorithms have a regularization parameter. So if you're going to get familiar with any of them, definitely get familiar with that. In particular here, we'll say this is multi-layer perceptron, so we're talking neural net. This is going to regulate how big your weights and biases get, because obviously we like to keep them quite small. And so this has an interesting effect when it's kind of jumping back and forward. And I think realistically this is because actually there's only 4 dimensions in this data set. So we're looking at 2 right now, about the petal width and the petal length, but there are actually sepal width and sepal length for anyone who doesn't know. So in a more dimensional data set, you're not going to have these geometric linear decision boundaries. You're going to have a much more curvy, swirly, whirly decision boundary. And you can actually see right now, I got a bit carried away with the parameter alpha. And I've made it bigger and bigger and bigger. And actually, the network gave up and said, oh, I'm just going to classify everything pink. I'm going to classify everything pink, blue, orange, black. I've given up, I'm done. So obviously, should be quite easy to pick up if you're monitoring your accuracy metrics or whatever evaluation metrics you have. But when hyperparameters go bad, they go bad. So realistically, what can we do to test out different values and to find the best values? So there's 4 methods I'm going to talk about today, and the first one is grid search. So grid search is kind of does what it says on the tin. This is your brute force search where you train a model under each combination of hyperparameters that you're interested in, and you evaluate how well it does. So this table, as an example, has 2 hyperparameters. So a C, maybe a regularization parameter, and a delta, which could be whatever. It might be distance, anything. And so if we want to test 5 values of each, obviously you have to multiply to get the total number needed to be checked, and that is 25 altogether. And so that's a conservative size, I would say, in general. But you can imagine as you get into 4 hyperparameters, 5 hyperparameters, you want to test 10, 20 values per piece. That scales exponentially. And so you can get into 1,000 models, 10,000 models, 20,000 models, which is not always feasible for kind of the average person who doesn't have high-performance computing or a fabulous GPU. So it can be a bit prohibitive, but you could say this is the gold standard because you're testing absolutely every value combination pair that you're interested in. You can parallelize this because you're creating and testing a model independently for each set of values. So that can be rather useful. And some newer strategies have a multi-resolution approach. So they take a sort of wider look at the general values that might be good, and then they zoom in towards smaller, like fine-grained ranges of values. A quick example to show actually kind of how easy this is to build in to your modeling, and this is an example from sklearn, which is is my favorite machine learning library, before Keras and TensorFlow. And all we have to do in the fourth line there is define our parameters. So there's 2 set out here in a dictionary. We also define the model we want to use, which is the next line down. Plug in both of those to a grid search method, and it will give us back the best hyperparameter set that it found for that model. So then we can take that forward into the final line, and we can properly train that to our data set. And there we have a predictor in 7 lines. I actually really do recommend the sklearn documentation. It's one of the things that really surprised me, because a lot of these libraries sometimes are lacking in their documentation. But I do really enjoy sklearns, because they also link to the appropriate publications and papers, so if you want to follow up with them, it's quite easy to do. So, in contrast to grid search, we have a randomized search, which is, again, as it says on the tin, if we have a massively large hyperparameter space we want to test, say that's 20,000 models altogether, your randomized search will pick however many of those at random and create and test those. So in here we have 100 model examples on the right-hand side. Each row will have a different random value for our 4 hyperparameters, and we'll track which ones perform best. When I first learned about this, I thought, that sounds like it's never going to work. So, not as hit and hope as you might think. There's many articles on the internet that test the performance of this versus grid search. We obviously do a comprehensive search. And so if you are computationally challenged, this is your best friend. It sounds like a bit of an insult, doesn't it? Well, he's computationally challenged. But a lot of us are. So, again, a few more lines of code, because we want to set up the different distributions that we want to sample from with our random search. So again, we have a hyperparameter set there as a dictionary in the middle. And we've got 5 hyperparameters in green. And then in the corresponding lists, we're defining the different values that we want to test from. Next line down, we're going to specify the number of iterations that we want. So that's the number of models. Just in the table that we saw, that was 100. And so we're being conservative here, and we're picking 20. And so this is how you can budget appropriately for the computational resources that you have available to you. And again, that can be parallelized, if you have facilities to do that. And again, passes back the best hyperparameters, and you go on and train your model with your training data. So, looks like a few more lines, but actually there's not much else to write. A useful one is built-in methods. So this recently popped up for me in sklearn. I don't know how long it's been available, but if you have estimators that just have a single hyperparameter like regularization, it's got a range of best practice defaults that it'll search for you as a built-in part of that estimator. So the easiest thing here is to look at an example. And so when we're setting our classifier in the middle there, we just call the algorithm, which is logistic regression. It's a very kind of good performing classifier. And I've written out all the different C's that we'll test here in this list. This is a little generator, I believe you'd call it in Python. And so we're generating values of 10 to the minus 4, 10 to the minus 3, 10 to the minus 2, blah, 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 all the way up to 10 to the 3, 10 to the 4. So these are the different magnitudes we're going to look at. And then it passes back the best parameters as before, and boom, fit, all good. So this saves us a couple of lines of code, which can be good. But as far as I'm aware, particularly in sklearn, this is only available for those that just have a single hyperparameter, because it doesn't perform exactly the same as, say, a grid search, because it implements slightly differently, so that is something to be aware of. Finally, is Bayesian methods. So imagine a combination between grid search and a random search. So we're not going to check all of the sets of hyperparameters that are possible. We're going to try and narrow in on the best ones and hope that those, or well, use those to model the probability that hyperparameters will improve our model. It's an interesting one. I haven't seen it used much. I think it's a current area of research, but I have heard that it can take a while, which isn't great when you're trying to conserve time. So there's a bunch of really good resources online where you can go and learn a bit more about this, but I don't know if we're terribly good at it yet. At least that's the feeling I got when I went to research around about it. However, I will admit that I don't know it inside and out. Hyperopt is the only Python library that I've seen consistently recommended to do it in. So if you're interested in that, that's the one to check out. So obviously you can overfit your data with this, which is not a good thing. But there are some strategies that we can take to minimize that, and we're going to talk about these 4 here. So cross-validation. All of the methods that we've looked at in sklearn have cross-validation built in, which is great. It is the best practice. If everyone hasn't heard of cross-validation, it's about slicing and dicing your data each time so that every single case gets a go at being a training or a testing set. And then you can have a mean test score that you can report with a standard deviation to get a more generalized view of realistic performance of your model. If you're not cross-validating at all, we need to talk. And actually, it needs to be part of a pipeline. So your training and test set should obviously be split appropriately. What you need to make sure and do is apply your transformations separately so that you don't leak data from one to the other. So as part of this, what we want to do is optimize our hyperparameters using cross-validation when we are, before we train our model, as part of training our model. And then we need to test them independently once we think we have the best hyperparameters, and go on to kind of critically evaluate how our model is performing. And again, more cross-validation can be employed at this second testing step. Using cross-validation for your hyperparameter search and for your overall testing of your best models called nested cross-validation. Again, you are adding to the time that you're going to take to test this, but to be honest, if you're not prioritizing the testing of your model, please don't make models. Not joking. If you're playing around, by all means, don't go into detail in terms of nailing all of your best practices first off the bat. You know, you do have to practice in not such a rigorous environment, but when you're talking about deploying models or using models to inform decisions, we need to be testing the crap out of those to understand really what they're doing. or to understand their behavior to the best of our current abilities. So, other than that, we do need to talk about evaluation metrics because they are not created equally. Something like accuracy is really intuitive because you can say, oh, that's 97% accurate on my test data. But actually, if you're in a multi-class scenario, much like the IRIS dataset, you don't know whether that 97% is equal across all classes. Is it skewed towards class 1, or is it massively imbalanced to class 2? So, something to do is actually consider using multiple metrics. And so actually you can often ask for a suite of metrics back. So like the commonly used classification metrics, for example. And so you can monitor different aspects of performance, which can be really useful. Things like rock space and similarity scores for classification. And when it comes to regression, mean squared error is very common, which is fine, but it can be quite hard to interpret. So something like your mean absolute error or a root mean square means that you're looking at an error that's comparable to the value of your data. So if you're predicting price, that means your error reported is going to be in price equivalence. It's much more understandable. R squared is also a really good one for regression. So how we can use this in terms of monitoring our different hyperparameter scores is to map, obviously, how it changes for our training set and for our validation set. So the two different lines here are actually very close, and you almost can't see them, which is great. Along the x-axis, we've got the different values of alpha that we're testing, and along the y-axis is the evaluation metric. And so you can see, as we progress along the x-axis towards me, we immediately fall off a cliff at some point, and our performance just nosedives. And so obviously that is where our hyperparameters don't want to be. And you can actually discern a lot about the performance of your training versus your validation set in terms of how close the lines are. If they're further away, it tells you a lot because it means it's doing better on one set than the other, which is not necessarily what you want because that can imply overfitting or underfitting. So these things are called validation curves. I definitely recommend them for monitoring your hyperparameter values. Automation. So this all sounds like a process that could well be automated. And you know, everyone wants to automate everything, which is great. But you still have to be aware of what could go wrong. So, I mean, I don't need to know how a car works. I don't need to know how to build a car in order to drive one. But I should really know the kind of signs and symptoms of my car not performing very well so that I can go and check it out. I think, realistically, automation of hyperparameter values is going to be the way we go, but I'm a control freak, so I don't really want to necessarily relinquish that in all scenarios. So I don't know if I'll be rushing forward to try those types of things out, but if that sounds like it's more for you, I would definitely make sure you understand what that piece of software is doing, because otherwise that can be, it can create kind of unfortunate models that you really don't want to run riot over your data. Or maybe, as a control freak, I'm a little bit biased. This is something that you have to find out for yourself if you're doing development or if your team are doing development. So, otherwise, what to do is, obviously, hyperparameters change on a per algorithm basis. So, whichever ones you want to use, look at what's available to tweak and tune and see what the best practice values are, because those will be initialized by default in probably your library of choice. Check out the documentation associated, for example, sklearn, as I've said, very good. You can go into the nitty-gritty papers, research papers that are associated with whichever algorithm you're using, but as someone who's looked at a lot of those papers, I do have to say they're quite math heavy. If that's not your thing, do feel free to avoid it, and because there's lots of other resources when it comes to blogs online. YouTube is a good one, and these are really reliable sources. They're not necessarily just Bob down the road who likes to do a bit of machine learning in his spare time. So don't feel like you have to always go to the kind of technical papers to get this type of information. So in reality, you are going to come across hyperparameters if you use machine learning. You do want to be able to tune them properly, otherwise things could go wrong. Don't hesitate to look around. Tutorials, YouTube, documentation, as I've said, to understand what they're doing to get an intuitive idea if you're not necessarily a maths person who wants to go and read papers. And yes, automation may come, but I always recommend never doing something blind. And so for now, I would definitely recommend consider a grid search, consider a random search, and see how you get on. And that concludes what we're talking about today. If anyone has any questions, I'd love to answer them.